October 29th, 2025. While most of Earth prepared for Halloween, something far stranger stirred in the depths of our solar system. On that date, Comet 3/ATLAS rounded the Sun at perihelion, diving to within 1.44 astronomical units of our star's surface. For most observers, the event passed in silence. At magnitude 9.5, the comet remained invisible to the naked eye, a ghost lost in the solar glare. Yet for those watching with patience and precision, October 29th marked something extraordinary: the awakening of an interstellar visitor after its closest brush with solar fire. There's an eerie poetry to what happened. This frozen traveler, born in the darkness between stars, suddenly found itself bathed in radiation intense enough to vaporize rock. In that moment, 3/ATLAS transformed. What had been dormant for millennia became active. Ice sublimated into jets. Dust lifted from ancient surfaces. A faint coma bloomed around its nucleus like breath condensing in winter air. The comet didn't just survive perihelion, it responded to it. Don't mind the Halloween prop rattling. That phrase, tossed casually across social media in the days following perihelion, carries more weight than its author intended. It captures something essential about 3/ATLAS. This cosmic visitor seems to perform on cue, as if the sun itself had pulled a string. The timing feels theatrical, a comet from another star, arriving just as humanity's instruments are sharp enough to study it, just as our understanding of plasma physics and cometary dynamics reaches new heights. It's a prank played on the solar system itself, an object responding to our star as if it had been here all along, as if it remembered the rules. But here's where wonder intersects with science. In the days surrounding perihelion, data began streaming in from observatories scattered across Earth and space. The numbers whispered of something unexpected. A coronal mass ejection launched from solar region 4246 on October 21st had propagated outward at roughly 1,000 kilometers per second. Its trajectory, when modeled backward, intersected 3/ATLAS's orbital path with unsettling precision. What happened when that wall of magnetized plasma collided with an interstellar comet? Nobody knows for certain. We weren't there to measure it directly. But the implications rippled through the astronomical community like a shockwave of their own. Two theories emerged almost immediately. The first, whispered in forums and amplified by headlines, suggested something far more sensational: alien technology responding to solar stimuli, a probe from another civilization using our sun's energy to power up after a long journey. The second theory, favored by professionals but no less fascinating, pointed to hypercharged comet physics, natural processes pushed to their extremes by the violence of the inner solar system. This isn't clickbait speculation. It's the modern echo of ancient sky myths, where unexplained lights demand explanation, and humanity projects its deepest questions onto celestial visitors. We stand at the intersection of data and wonder, watching numerical patterns emerge from the darkness, trying to distinguish signal from noise, physics from fantasy. For several crucial days following perihelion, 3/ATLAS vanished, not because it disintegrated or flew apart, though such fates are common for comets approaching the sun, but because it disappeared behind the solar limb from Earth's perspective. Our planet's greatest telescopes, instruments capable of detecting objects billions of light years away, were suddenly useless. The comet had entered a blind spot, a region where solar glare overwhelms even the most sensitive detectors. Ground-based astronomy fell silent. For those tracking 3/ATLAS, the days after October 29th became an exercise in patience and trust. Trust that the comet still existed. Trust that their calculations held true. But space doesn't care about human limitations. While Earth-bound instruments waited in frustration, spacecraft positioned throughout the solar system continued their vigil. The Punch mission, designed specifically to image the sun's corona and solar wind structures, maintained its steady watch. From its unique vantage point, Punch could observe regions invisible from Earth. Its cameras captured faint signals, stacking exposures over hours and days, accumulating photons one by one. And gradually, almost reluctantly, a pale glow emerged from the noise. The comet was there, steady, dimension, but undeniably alive. Cinematically, imagine this as a heartbeat detected under surgical lighting. Each stacked frame represents a pulse, proof of survival where none was guaranteed. Scientists monitoring the data feeds held their breath, not from superstition, but from professional understanding. Comets that survive perihelion passages this close demonstrate structural resilience rare among small bodies. They're not loose rubble piles held together by ice and hope. They're coherent objects with enough internal strength to withstand tidal forces that would shred weaker structures. Every pulse of light from 3I/ATLAS confirmed something profound. This interstellar visitor possessed the durability to endure our sun's violence. The solar glare created more than observational difficulties. It represented a fundamental gap in human knowledge, a period where models replaced measurements, where scientists had to trust equations more than eyes. In those days of blindness, uncertainty bloomed. Was the comet brightening as predicted? Had the CME stripped away its nascent atmosphere? Did the nucleus remain intact, or had thermal stress fractured it into fragments? These questions hung unanswered, suspended in the liminal space between theory and confirmation. November arrived with a gift: geometry. As Earth continued its orbital dance and 3I/ATLAS crawled outward from the Sun, elongation, the angular distance between comet and star, began to widen. 30 degrees, 35, 40. Each degree represented better observing conditions, less contamination from solar light. Amateur astronomers across the globe turned their telescopes toward the pre-dawn sky, squinting into the twilight murk, hunting for a signal they'd only seen in predictions. The first catches were barely there, noisy pixels smeared across CCD sensors, faint smudges that could have been comet, artifact, or wishful thinking. But astronomers know this dance. They compare coordinates, cross-reference timing, debate the nature of each detection with the scrutiny of forensic analysts. Is that 14th magnitude dot in the expected position? Does it move at the correct angular rate? Do multiple independent observers see it at the same time? Confirmation doesn't come from a single image. It emerges from consensus, from the triangulation of data across continents and instruments. International observatories synchronize their efforts. Japan's networks, Chile's desert arrays, the pristine skies of La Palma all contributed pieces to the puzzle. Each detection added confidence. The coordinates aligned. The motion matched predictions. The brightness held steady near magnitude 9 to 10, varying slightly but remaining consistent with a comet in the process of gentle outgassing. One truth crystallized from scattered photons. 3I/ATLAS had survived. It remained intact. The visitor from interstellar space continued its journey through our solar system. But beneath the relief lurked something curious. The trajectory refused to align perfectly with gravitational predictions. Minute deviations appeared in the orbital solutions, tiny discrepancies between where the comet should be and where observers actually found it. These weren't errors, they were signals. Something beyond gravity was influencing 3I/ATLAS's path. Something subtle but measurable, something pushing it, just slightly, off its predicted course. For those familiar with comet science, the explanation arrived immediately: non-gravitational forces. When a comet heats, ice sublimates asymmetrically. Jets of vapor erupt from the sunlit hemisphere, each burst creating a tiny thrust, a miniature rocket effect. Multiply these microscopic pushes across billions of particles and millions of kilometers, and the cumulative effect becomes significant enough to alter trajectories. This isn't mysterious, it's standard cometary physics. But for 3I/ATLAS, an object that had spent countless millennia in the frozen depths of interstellar space, watching these forces awaken felt like witnessing resurrection itself. The mathematics of cometary motion occupy a strange territory between precision and chaos. When Isaac Newton derived his laws of gravitation, he gave humanity the power to predict celestial positions with breathtaking accuracy. But comets refuse such clean obedience. They leak, they push. They writhe against gravity's grip with forces invisible yet undeniable. Enter JPL's A1 and A2 parameters. These aren't mysterious constants or evidence of anomalous physics. They're quantified descriptions of non-gravitational acceleration, measurable effects produced when sublimating ice creates thrust. A 1 represents radial acceleration, forces directed toward or away from the sun. A 2 captures transverse acceleration, pushes perpendicular to the sun-comet line. Together they describe how vapor jets alter momentum momentum over time. For 3I/ATLAS, preliminary orbital solutions suggest A1 values around 10 to the -8 astronomical units per day squared, subtle but detectable across months of observation. Think of it this way: each molecule of water ice that sublimates from the comet's nucleus carries momentum. When it escapes into space, it pushes back against the nucleus according to Newton's third law. One molecule's push is negligible. But when trillions of molecules sublimate per second, distributed unevenly across a rotating, irregularly shaped nucleus, the cumulative thrust becomes measurable. It's like steering an aircraft carrier with a collection of battery-powered fans, absurd on its face, but given enough time and distance, capable of producing detectable course changes. The beauty lies in the physics itself. Solar radiation heats the sunward hemisphere more intensely than the night side. Thermal lag means the hottest point on the nucleus isn't directly under the sun, but slightly offset, rotated ahead by the nucleus's spin. Sublimation peaks at this hot spot, creating jets that fire at an angle relative to the Sun-Comet line. These angled jets produce torque as well as thrust, potentially altering the nucleus's rotation state while simultaneously changing its trajectory. It's a delicate, chaotic dance of thermodynamics, fluid dynamics, and orbital mechanics. JPL's official phrasing captures this elegantly: standard cometary physics made extreme by solar-wind interaction. The professionals aren't puzzled by 3I/ATLAS's behavior. They're awed by it. Every measurement refines their understanding of how comets respond to solar heating. Every deviation from pure gravitational motion reveals information about the nucleus's shape, composition, rotation, and thermal properties. Alien speculation thrives in the gaps between public understanding and professional knowledge, but for those tracking the data, 3I/ATLAS performs exactly as a comet should. It's just doing so with the intensity expected from an object experiencing our sun's fury for the first time in millions of years. This isn't less fascinating because it's natural. If anything, it's more so. Physics performing miracles of balance under solar violence, matter and energy locked in perpetual negotiation. A frozen mountain from another star learning to breathe in the warmth of our sun. The equations describe it. The observations confirm it. The wonder remains. Shift perspective now, from orbital mechanics to plasma physics, from the comet as a gravitating mass to the comet as an electromagnetic phenomenon. Around 3I/ATLAS, invisible to optical telescopes but blazing in ultraviolet and X-ray wavelengths, exists a plasma cocoon, a dynamic, breathing skin where matter exists in its fourth state, where electrons roam free from their parent atoms, where magnetic fields twist and ripple like fabric in wind. This plasma environment emerges from 5 fundamental processes, each contributing to the comet's electromagnetic identity. First, photoionization. Solar ultraviolet radiation carries enough energy to strip electrons from neutral gas molecules. A water molecule evaporating from the nucleus enters sunlight as H2O, stable, electrically neutral. Photons slam into it, tearing away electrons, transmuting it into H2O+, an ion now responsive to magnetic fields. What was once subject only to gravity suddenly feels the electromagnetic force, reacting to the solar wind's magnetized plasma like iron filings responding to a magnet. Second, charge exchange. This process occurs when solar wind ions collide with neutral comet gases. A proton from the sun's wind already ionized encounters a neutral molecule and steals an electron. The roles reverse. The solar wind ion becomes neutral. The comet gas becomes ionized. This electron theft happens constantly throughout the coma, creating a mixed population of ions with complex energy distributions. When charge exchange produces energetic neutral atoms, those particles carry information about the solar wind's composition and temperature, information that spacecraft instruments can decode. Third, mass loading. As ions created through photoionization and charge exchange accumulate in the coma, they add mass to the local plasma environment. The solar wind, streaming outward at hundreds of kilometers per second, suddenly encounters this population of slow-moving ions. The solar wind can't simply pass through. It must accelerate these ions, dragging them along, expending energy and momentum in the process. This mass loading acts like a brake on the solar wind, creating a region where the solar wind slows and deflects around the comet rather than passing directly through it. Fourth, bow shock formation. When mass loading becomes significant, the solar wind's supersonic flow creates a shock wave upstream of the comet, a bow shock analogous to the sonic boom produced by supersonic aircraft. Ahead of this shock, the solar wind remains fast and tenuous. Behind it, the wind slows, heats, and compresses. The bow shock represents the comet, announcing its presence to the solar wind, a region where kinetic energy converts to thermal energy in a turbulent, plasma-churning boundary layer. Fifth, the ionopause. Deep within the plasma environment, where newly created ions reach maximum density, the magnetic field carried by the solar wind cannot penetrate. The ionized coma generates its own magnetic pressure, excluding the solar wind's field and creating a boundary called the ionopause. Inside this boundary, the comet's plasma dominates. Outside, the solar wind reigns. The ionopause breathes, expanding when solar wind pressure drops, contracting when CMES compress the entire magnetized structure. Together, these 5 processes create an invisible architecture around 3I/ATLAS, a dynamic structure larger than Earth but imperceptible without specialized instruments. In ultraviolet images, this structure glows softly, emission from excited atoms and molecules radiating photons as they cascade to lower energy states. In magnetometer data, it appears as compressed field lines and turbulent fluctuations. It's the living skin of the comet, where sunlight sculpts matter into plasma, where chemistry becomes electromagnetism, where invisible weather rages in silence. Viewers must understand the scale here. This isn't merely a rock with ice. 3I/ATLAS has become a moving laboratory for plasma physics, a natural experiment in magnetohydrodynamics unfolding in real time across millions of kilometers. Every second, the comet loses mass. Every second, new ions form. Every second, the balance between internal plasma pressure and external solar wind pressure shifts. The phrase plasma cocoon becomes more than metaphor. It's both protection and volatility, a shield that pulses with the rhythm of solar activity. Now descend to the smallest actors in this drama, dust grains liberated from the nucleus by sublimating ice. These particles, ranging from nanometers to millimeters in diameter, represent the solid remnants of the comet's birth. Silicates, organics, carbon compounds, perhaps even pre-solar grains older than our solar system itself. As they lift from the nucleus surface, carried by expanding gas, they enter an environment utterly hostile to solid matter. Solar ultraviolet radiation doesn't just heat these grains, it electrifies them. Photons strike grain surfaces with enough energy to eject photoelectrons, leaving the grain positively charged. Other grains, shadowed from direct sunlight or immersed in the electron-rich inner coma, accumulate negative charge. Now these particles don't merely move under gravitational and gas drag forces. They respond to electric fields. Charged grains repel each other. They spiral along magnetic field lines. They experience Lorentz forces that can accelerate them to unexpected velocities. But something more violent can occur: electrostatic fragmentation. When a dust grain's surface charge becomes sufficient, electrostatic repulsion between adjacent regions of the grain can overcome the cohesive forces holding it together. The grain shatters, not from collisions, not from thermal stress, but from its own accumulated charge. These micro-explosions happen invisibly, fragmenting parent grains into clouds of daughter particles. Each fragmentation event creates a burst of newly exposed surface area, increasing the total cross-section available for scattering sunlight. This matters enormously for brightness measurements. When observers report that 3I/ATLAS brightens slightly, they may be witnessing the integrated effect of countless dust fragmentation events. Each shattered grain contributes additional scattered light. The comet appears to flare, not because activity increased, but because existing dust suddenly multiplied its light-scattering efficiency through electrostatic shattering. ESA's Rosetta mission provided the template for understanding this phenomenon. At Comet 67P/Churyumov-Gerasimenko, Rosetta's instruments detected sudden coma brightness increases that correlated with dust fragmentation events. Over the course of a single night, the inner coma's optical properties changed dramatically. Dust that had appeared homogeneous revealed itself as dynamic, fragmenting under radiation pressure and electrostatic stress. What seemed like supernatural flickering was, in fact, high-energy chemistry occurring at the intersection of sunlight and matter. For 3I/ATLAS, each observed brightness variation could trace back to these dust dramas. The comet doesn't blink randomly. It blinks in response to the solar environment, to the arrival of energetic particles, to the accumulation of charge on dust surfaces. What we interpret as a magnitude surge might represent a microscopic storm of shards spiraling through magnetic tides. A storm we read as a simple number, brightness up by 0.3 magnitudes. Behind that number lies physics elegant and violent. Chemistry played out at nanometer scales with consequences visible across astronomical units. Now we reach the heart of the mystery, the October 21st coronal mass ejection and its potential collision with 3I/ATLAS. To understand what might have happened, we must first travel backward in time to June 14, 2015, and visit a different comet orbiting a different star. Comet 67P/Churyumov-Gerasimenko, monitored by ESA's Rosetta spacecraft, experienced something extraordinary that day. A moderate CME launched by the Sun propagated outward and slammed into the comet's magnetosphere. Rosetta's magnetometer recorded the impact in real time. The comet's induced magnetic field, previously holding steady around 50 nanoteslas, suddenly surged. 60 nanoteslas, 100, 200. The field peaked at nearly 300 nanoteslas, a six-fold amplification in mere minutes. Imagine the scene aboard Rosetta. Data streams from the magnetometer suddenly spike. Alarms trigger as measured values exceed expected ranges. Scientists monitoring the telemetry feed watch numbers climb in real time, trying to comprehend what they're witnessing. This wasn't instrument malfunction, this was nature demonstrating the violence possible when solar weather collides with cometary plasma. The physics behind this surge involves magnetic field compression. The CME arrives as a wall of magnetized plasma traveling at hundreds or thousands of kilometers per second. When it encounters the comet's plasma environment, it compresses the existing magnetic structure like a vice-crushing foam. The comet's induced magnetic field, generated by the interaction between the solar wind and the ionized coma, intensifies proportionally to the compression. Meanwhile, the CME's own embedded magnetic field adds to the local field strength. The result? A temporary but dramatic surge that reconfigures the entire plasma environment. For 67P, the consequences included tail disconnection. The comet's ion tail, magnetically connected to the solar wind, suddenly severed. Magnetic field lines that had been orderly and extended snapped under stress, triggering magnetic reconnection events. Plasma that had been flowing smoothly down the tail suddenly found itself disconnected, adrift, forming luminous knots and filaments visible in ultraviolet images. The comet bled plasma into space, a wound that took hours to heal as new magnetic connections slowly re-established themselves. Now extrapolate this scenario to 3I/ATLAS. On October 21st, 2025, solar region 4246 erupted, launching a CME with propagation speeds near 1,000 kilometers per second. Tracking this ejection forward through space and time, models suggest it would have reached 3I/ATLAS's orbital position around October 23rd to 24th, mere days before perihelion. The geometry aligns eerily well, the speeds match, the trajectory intersects. What happened when that magnetic wall hit an interstellar comet approaching peak activity? We don't know with certainty. No spacecraft orbited 3I/ATLAS to measure the impact. No magnetometer recorded field strength spikes. But we can model, extrapolate, and imagine based on physics proven at 67P. Probable consequences include sudden compression of the plasma sheath around the nucleus. The bow shock, if it had formed, would have lurched inward as solar wind dynamic pressure spiked. Magnetic field lines threading the coma would have twisted and compressed, storing energy that could later release through reconnection. Ion production rates, already elevated by perihelion's intense ultraviolet flux, might have surged further as the CME's enhanced radiation ionized more gas. Dust grains, electrostatically charged, could have fragmented en masse as fields intensified. And the tail, if 3I/ATLAS had developed one by this point, might have disconnected. Observers saw no dramatic tail structures before or after perihelion, but geometry matters. If the tail pointed away from Earth or remained too faint to detect from our vantage point, a disconnection event could have occurred invisibly, plasma streaming away into the solar wind's embrace while we searched blind behind the solar glare. The most haunting part isn't what we observed, it's what we couldn't. The CME impact likely occurred precisely when 3I/ATLAS vanished behind the Sun from Earth's perspective. We were blind. The violence happened in darkness, from our point of view. Somewhere in the empty space between Mercury and Venus, an interstellar comet felt the Sun's rage concentrated into a magnetic hammer blow, and we could only model, calculate, and wait for the comet to emerge into visibility again, searching for clues written in its post-impact brightness and trajectory. The sun blinked and an interstellar comet flinched. If our models hold true, that moment represents one of the most significant plasma events involving an interstellar object that humanity has ever indirectly witnessed. In the absence of direct spacecraft measurements, astronomers become detectives. They piece together narratives from fragments, a brightness measurement here, a positional observation there, spectroscopic data if fortune smiles. Each data set is incomplete, like shards of a mirror, each reflecting one facet of truth but none showing the complete picture. For 3I/ATLAS, the constraints are frustrating. The tail, if present, remains unresolved in most observations. Ground-based telescopes struggle to separate nucleus from coma. The comet's rotation period stays uncertain. Observations haven't captured enough brightness variations to definitively determine spin state. The nucleus shape remains unknown. Is it an elongated ellipsoid tumbling end over end? A contact binary held together by gravity? A rubble pile barely coherent? Each possibility produces different predictions for activity patterns and non-gravitational forces. Yet science thrives in this uncertainty. Forensic astronomy doesn't require perfect data. It requires rigorous method. Scientists test each hypothesis against every available constraint, discarding models that contradict observations, refining those that survive. The process is iterative, provisional, and honest about its limitations. No astronomer claims certainty when dealing with incomplete data sets. Instead, they speak in probabilities and confidence intervals, inconsistent with and ruled out. Consider the faintness issue. At magnitude 9 to 10, 3I/ATLAS appears dimmer than some predictions suggested. Two broad explanations compete. First, intrinsically low activity. Perhaps the nucleus contains less volatile ice than typical comets. Perhaps thermal lag prevents efficient sublimation at this heliocentric distance. Perhaps the rotation axis orients such that the most volatile-rich regions remain in shadow. Each of these scenarios produces a faint comet through natural, well-understood physics. Second, environmental stripping. The CME impact and intense solar wind at Perihelion might have stripped away the nascent coma, removing the gas and dust that scatter sunlight. After the impact, activity would resume, but the coma would take time to rebuild. Observers measuring brightness days after perihelion would catch the comet in a depleted state, dimmer than it would have been without the disturbance. Both scenarios remain viable. Both fit the limited data. Distinguishing between them requires more observations. Spectroscopy to measure gas production rates, dust analysis to characterize grain size distributions, photometry across multiple nights to detect subtle variations. Each new data point shifts the balance of evidence slightly, favoring one model over another, until eventually a consensus emerges. This is forensic astronomy. It acknowledges what we don't know while extracting maximum information from what we do. It treats each observation as testimony, reliable within error bars but never absolute. It builds cases rather than declarations, assembling evidence into coherent narratives while remaining ready to discard those narratives if better data demands it. For 3I/ATLAS, the investigation continues. Every observation adds context. Every measurement refines orbital solutions. Every spectrum reveals composition. We may never know exactly what happened during the blind spot behind the sun, but we can constrain possibilities, rule out impossibilities, and build increasingly accurate models of an event we couldn't directly witness. That's the power and humility of science. Each provisional truth waits patiently to be overturned by better light. November and December 2025 bring opportunities. As 3I/ATLAS's elongation increases and geometry improves, observing windows expand from fleeting pre-dawn glimpses to sustained tracking across multiple nights. November 4th, elongation reaches 29 degrees. The comet clears the worst of the solar glare, visible now in dark twilight for experienced observers with properly calibrated instruments. Brightness hovers near magnitude 10, faint, but within reach of dedicated amateur astronomers equipped with 8-inch or larger telescopes and CCD cameras. Each image captured during this window becomes scientifically valuable, contributing to the extended ephemeris that JPL will use to refine orbital solutions. November 14th, elongation exceeds 50 degrees. Now the comet rides higher above the horizon at dawn, accessible to a broader range of instruments. Observatories begin sustained photometric monitoring, tracking brightness variations night after night, searching for periodic signals that might reveal rotation. Spectrographs attempt compositional analysis, hunting for emission lines from CN, C2, and C3, diagnostic molecules that betray the comet's chemical heritage. December 19th. closest approach to Earth. At one point, 8 astronomical units, roughly 270 million kilometers. This represents our best opportunity for detailed study. The comet won't be visually spectacular. Magnitude predictions suggest it will brighten only to magnitude 8 or 9, still below naked eye visibility. But for professional instruments, this proximity offers angular resolution unavailable at greater distances. Nucleus size estimates improve. Tail structure becomes easier to resolve. Non-gravitational accelerations refine as positional uncertainties shrink. January 9th, 2026. Planetary alignment. On this date, Venus, Earth, and 3 I/ATLAS arrange themselves in a rare geometric configuration that some online sources claim holds significance. Let's be clear, planetary alignments don't cause anything. They don't trigger cometary outbursts or alter trajectories beyond the negligible gravitational perturbations already included in orbital models. But geometry does matter for observation. Alignments can provide useful reference points for orbital calibration, allowing astronomers to measure positions relative to Venus's well-known orbit, reducing uncertainties in 3 I/ATLAS's ephemeris. The contrast between scientific value and viral speculation couldn't be sharper. Online alignments breed prophecy. Articles claim the configuration will activate the comet or reveal its true nature. In observatories, astronomers see it differently. They recognize January 9th as a date when geometry simplifies certain calculations, when reference objects align conveniently for astrometry. The comet cares nothing for our calendars. It obeys gravity and thermodynamics. Indifferent to numerological significance, we project onto celestial arrangements. For serious observers, these dates represent a narrative arc. November brings recovery from solar blindness. December brings proximity and resolution. January brings geometric convenience. But the real story unfolds in accumulated data. Thousands of images stacked into light curves, hundreds of spectra revealing compositional secrets, dozens of astrometric positions constraining the orbit with increasing precision. Patience defines this phase of observation. The comet will not blaze across our sky, trailing vast, luminous structures visible from cities. It will remain a faint smudge, unremarkable to untrained eyes, nearly invisible without optical aid. But in its dimness, data burns brighter than rumor. Each photon captured by a telescope sensor carries information about the nucleus, about the coma, about plasma interactions, about the deep past of an object that formed in another star's planetary system and has now, by chance or chaos, entered ours. Real beauty lies in precision, in a faint signal caught by disciplined eyes, measured by calibrated instruments, analyzed by minds trained to distinguish physics from fantasy. October 29th, 2025 wasn't an omen. It was a milestone in humanity's expanding dialogue with the cosmos. On that date, an object born in another star's planetary system reached perihelion around our sun, survived, and continued its journey. The event occurred whether or not we watched, whether or not we understood, whether or not we cared, but we did watch. We did attempt understanding. And in that attempt, we added another chapter to the story of how matter moves through space, how physics operates across interstellar distances, how even visitors from beyond the solar system obey universal laws. 3 I/ATLAS is both ordinary and extraordinary. Ordinary because it behaves exactly as cometary physics predicts. Outgassing, developing non-gravitational accelerations, responding to solar radiation and plasma interactions according to well-established models. Extraordinary because it carries with it the story of another stellar environment, another planetary system's formation and evolution, another set of initial conditions we can barely imagine. Let's recap the key takeaways with narrative gravity. Perihelion occurred at approximately 1.44 astronomical units on October 29th. Peak brightness reached magnitude 9.5, faint but measurable. A1 and A2 parameters indicate non-gravitational forces consistent with natural comet outgassing, showing no anomalies that would suggest anything beyond standard physics. The October 21st CME likely impacted the comet's plasma environment between October 23rd and 24th, potentially causing magnetic field compression, plasma stripping, and tail disturbances that we couldn't directly observe. The tail remains weak or unresolved, likely due to a combination of viewing geometry, intrinsic low activity, and possible CME-related stripping. Closest approach to Earth occurs December 19th at 1.8 astronomical units. Extended observations continue through early 2026. What does this mean philosophically? The allure of alien explanations reveals something profound about human psychology. We hunger for significance. We want to believe that strange lights in the sky carry messages, that visitors from other stars come bearing purpose. This hunger isn't irrational, it reflects our deep need to find ourselves part of a larger narrative, to discover that intelligence exists beyond Earth, that the universe contains minds capable of recognizing other minds. But the reality of physics reveals a deeper awe. That matter from another star behaves exactly as equations predict. This is the true miracle, that we can observe an object formed around a different sun, potentially millions of years ago, and understand its behavior through principles discovered in terrestrial laboratories. This is the extraordinary part. No aliens needed. No mysterious technology required. Just matter and energy, interacting according to laws that appear universal, that transcend stellar systems and galactic neighborhoods, that connect 3I/ATLAS to every comet humanity has ever studied. Science doesn't diminish wonder. It transforms wonder from vague mysticism into precise appreciation. When you understand that each photon of light scattered from 3I/ATLAS began its journey at the sun, traveled across 1.44 astronomical units in 8 minutes, reflected from dust grains older than Earth, and reached your telescope sensor to be counted and measured, this chain of causation inspires reverence more profound than any fantasy about alien probes. The comet didn't vanish, it evolved. From dormant interstellar iceberg to active comet, from invisible visitor to measured object, from mystery to data. And for those who measure instead of imagine, 3I/ATLAS continues speaking, one photon at a time. Across Earth, telescopes turn eastward as dawn approaches. In Chile's Atacama Desert, in Japan's mountain observatories, in Spain's Canary Islands, instruments slew toward precise coordinates. CCDS cool to operating temperatures. Spectrographs calibrate. Computers prepare to stack exposures, extracting signal from noise with algorithms refined over decades of cometary observation. Somewhere above the horizon, invisible to naked eyes but blazing in telescope fields of view, 3I/ATLAS continues its journey. It has rounded the sun. It has felt solar fire for the first time in eons. It has awakened, responded, and survived. Now it retreats back toward the outer solar system, climbing away from the sun's warmth, eventually escaping back into interstellar space to resume the long, cold voyage it began before our species existed. But in this brief intersection of trajectories, comet and civilization, visitor and witness, we gain something invaluable. Not proof of aliens, not confirmation of supernatural powers, but deeper understanding of how nature operates at scales both intimate and cosmic. Every measurement of 3I/ATLAS improves our models of cometary physics. Every spectrum reveals clues about planet formation in other stellar systems. Every detected non-gravitational force refines our ability to predict trajectories and understand orbital evolution. The data accumulates, the models improve, the mystery resolves into physics, not in one dramatic revelation, but in the patient accumulation of evidence, the gradual convergence of observations toward consensus. This is how science works, not through epiphanies but through diligence, not through genius but through rigor, and still the comet speaks. For those with ears to hear, or rather eyes to see and instruments to measure, 3I/ATLAS remains eloquent. Its brightness variations tell stories of rotation and activity. Its trajectory reveals the interplay of gravity and thrust. Its spectrum betrays its composition and origin. Every night it's visible, astronomers add to the record, building a portrait of an interstellar traveler caught in our sun's temporary embrace. We will lose it eventually. As 3I/ATLAS recedes past Jupiter, past Saturn, past the edge of easy observation, it will fade from magnitude 10 to 15 to 20, eventually becoming too faint for all but the largest telescopes. One day it will wink out entirely from human sight, resuming its journey into darkness, but the data remains, the measurements endure, and when the next interstellar visitor arrives, and there will be another, we'll understand it better, because of what 3I/ATLAS taught us. This is the bigger picture. Not a single comet on a single date, but the ongoing conversation between humanity and the universe. A conversation conducted in photons and equations, in orbital elements and spectral lines. A conversation that asks not, are we alone, but rather, can we understand? And tentatively, measurement by measurement, the universe answers, yes, you can understand. The laws I obey are knowable. The patterns I follow are decipherable. Learn them, study them. I am not random, I am not capricious, I am physics. And somewhere in that answer lies a wonder deeper than any myth, more satisfying than any prophecy. The wonder of comprehension, the awe of understanding, the profound privilege of being a species capable of measuring starlight and extracting meaning. 3I/ATLAS woke up after perihelion, and in its awakening, we saw ourselves more clearly, a curious species, standing on a small planet, reaching out with instruments and imagination to touch the universe beyond. Not gods, not masters, but witnesses, students, participants in a cosmos vast beyond comprehension, yet intelligible through patience and precision. The comet continues, the measurements continue, and for those who watch with clear eyes and open minds, the universe continues its greatest gift, the gift of being knowable.